Thank you. So what if I told you that MongoDB has purpose-built native support for time series? What if I told you that MongoDB has an optimized storage format that saves you money? And what if I told you that it takes almost no time to set up? I'm going to answer these questions, but before I do that, let me just introduce myself. I'm Danilo Nobrega, as mentioned. I'm a solutions architect, and I've been working with a number of customers over the past 2 years that use time series. And Michael and Louis, to give them credit, are the ones that actually have worked implementing this and releasing the features, so shout out to them. They've, in the past year, have been talking to a number of customers and users like yourselves to understand what works with MongoDB and what doesn't for time series, along with purpose-built solutions. And we've set out from 5.0 onwards to build, to make it easier, faster, and less expensive to build time series applications on MongoDB. So I'm going to go through this presentation talking about what time series is, some of the challenges, what are the challenges to build time series applications, and how MongoDB solves some of those problems, and why ultimately you should use MongoDB time series collections. So what is time series data? Time series is a sequence of measurements over a period of time. But that data has typical properties that make it special and ultimately challenging to work with. So some of the properties is the ingested data is keyed by time. It's typically very high ingest rates. The raw retained data volumes are high. It's generally ordered and append heavy with minimal updates. Apart from the properties, there are usage patterns as well, such as cold raw data is infrequently accessed and often archived. Queries often rely on heavy use of time-based filters. Analytical queries are performed over period roll-ups. And queries are also using window functions such as moving average, running sum, or year-over-year average. And what are some of the use cases for time series? Well, time series data is everywhere. It's generated on the heart sensor of your smartwatch by embedded IoT devices. It's used in financial markets, when you trade crypto, for example, fleet monitoring. And so it's basically everywhere, and most likely than not, you have use cases that could use time series right now. So although time series is straightforward to understand and the use cases are vast, there are many challenges building time series applications. If you're using a traditional relational database, for example, you will come across the rigidity of the schemas and also the challenge in limited platform integrations and inefficient processing of the data volumes generated. You also have purpose-built databases for time series that solve some of the problems from relational databases, but they also introduce some problems of their own, such as difficulty scaling, management of the data lifecycle. So since these solutions, they don't have access to the underlying controls of the database, they often rely on integrations of external tools, and that makes it hard to manage archival, for example, of data. You have to use external solutions for that. And then last but not least, you cannot do in-place analytics. You have to move your data to combine data that has been archived and from the real-time time series. So from MongoDB 5.0 onwards, we've introduced a native time series platform. And the main idea is to make it extremely easy to use. So it's a new collection type called time series collections. And it's optimized for time series data, basically. So behind the scenes, we create a clustered index to optimize the index size and also make it very fast for read access. And we have launched two different analytical capabilities, the window functions and also temporal operators to work with time series data. Last but not least, when you use time series on MongoDB, you get access to a platform. So we handle the ingestion all the way to the archival, and throughout you can do native visualization, for example, using charts. So how do these time series collections work? To create the collection, you just pass the new time series field, and inside that time series field, you will specify which field in your document you want to use as the timestamp. It has to be of date type. That's because we order the data behind the scenes to make it more efficient. And this is also how we handle out of order or late inserts. What about inserting data? Just like inserting data in regular collections, note here I have 3 documents generated by a temperature sensor, and I'm using insert many for batch inserts, and also the unordered write API to make my writes as fast as possible. How do you query data in time series collections? Here I'm doing a find, and you see that as a result, I have the documents I have inserted previously. So super easy, but this example is quite simple. What if I had more sensors? What if my data model was more complex? Or what if my data was inserted late or out of order? And that's where the configuration options come in. The first option I'm going to talk about is metafield. So metafield identifies the time series. You can think about it in terms of when you plot time series on a chart, you can see there I'm plotting 3 different IDs. So the metafield would identify those. And it needs to be correlate, or you need to think about your query patterns when you create the metafield, because it will have an impact on the performance of your queries. The data will be stored grouped together for that given sensor, for example. In 5.1, we've introduced as well deletes and updates from time series collections. So here you can perform updates and deletes on the metafield values. And this is also working with 5.0. This is an example of a delete. You use the delete many command. And in the match expression, that needs to be a match with the time, with the metafield. And in this case, I'm matching sensor 1 to 3. So all of the documents for sensor 1 to 3 will be deleted. Okay. Granularity is another option. And this is depending on your use case, your data might come in faster or slower intervals of time. So let's say if you're working with stock tickers, data is arriving every second. If you're working with cargo fleets, the trucks might be arriving in minutes, every minute. If you're working with weather data, it might be hours. So you can set that when you create the collection, and that basically makes it more efficient. It also, the coarser the granularity, the better support for out of order data, just because you have more time, you have more of a buffer to store the data that's out of order together. This can be modified as well later on if you don't get it right. If you think that you should increase to a coarser granularity, you can change that with call mod, but it can only go from seconds to minutes or minutes to hours, not the other way around. Expire after seconds is another one, and this is if you want to efficiently delete your data after a period of time. So some data is like milk. It has lower value once it ages, so you might not want to keep storing that in a highly performant cluster. And so just by setting the time, in this case it's 1 day, expressed in seconds for expire after seconds, the data will be deleted very efficiently because it's stored in order by time, so we can do that really efficiently. Again, this can be modified with call mod. If you have a bit more technical background, you might be wondering how the data is stored behind the scenes, how this optimization works. Basically, you have 3 sections. The metadata is only stored once, and here we will create at least 1 document per unique metadata. And then inside that document, we will group the measurements for that metadata, and we will group it in sequence, the measurements of time. And in the control section, we will store aggregations for those measurements that are useful for us. Now, if in this case I only have 1 sensor from New York, I have all the measurements, it's only 1 document, so a lot of documents that are inserted is grouped into 1 document behind the scenes. If my data grows, more documents are created, and I will have as many documents as sensors or unique metadata IDs that I have in my collection. This is another view of the internal optimization. Again, you see the metadata is stored once. The data is stored sequentially. Here we have just simple values, but you can also store documents or arrays, for example. So we have the flexible schema there that can be used. If no measurement exists, if no value exists for a measurement, then we don't store anything, so it's very efficient. And in the control, we always store for every measurement the minimum, maximum value, and we do that for time as well. And behind the scenes, the primary index is on time, so it's the underscore ID, and it's different if you use to MongoDB to the underscore ID that you usually have in a collection. This is generated internally, automatically, and you don't even view this index, it's hidden. So these grouped documents, they have some limits to the lesser of 1,000 measurements or 4 megabytes of space, or to the maximum time span controlled by granularity. If it exceeds any of those, a new document is created. So to summarize, time series collections support out-of-order data. We can use flexible schemas for the measurements. It doesn't only have to be simple values, it can be arrays, objects. You have efficient storage for missing data because we don't store values that are missing. And that enables us to have efficient queries and also efficient indexes. And talking about the indexes, let's have a closer look at how this works. We index the measurements in groups, not individually, and this allows us to dramatically reduce the index sizes. So for example, if you were to query on station and time, you would create a compound index on station and time. If you were just querying on a metadata subfield, you would create an index for that. That would identify a unique station, for example. So these indexes you can also do now with 5.1 2D and 2D sphere index on the metadata. So as I told you, time is the primary, and you can create secondary indexes on meta fields and meta subfields. And so with the 2D sphere, you might want to use it for stationary sensors or a sensor that stays put for periods of time. And this supports queries that calculate geometries on Earth-like sphere, or queries for inclusion, intersection, or proximity. In this case, it's a very simple one. My metadata is just the location, and I created the index on location here. Sharding, this was announced earlier today, so now we support sharding on 5.1 and 5.0. And why would you shard a time series collection? Well, if you have high cardinality use cases, such as a million concurrent time series, then you would shard to spread out the data and avoid clumping of data. If you need more storage capacity, more shards, more disks. If you need to increase the throughput of reads and writes, so more shards, more CPUs, more IOPS, more network bandwidth. If you need to decrease the latency of reads and writes, so more shards, more RAM, bigger working sets possible, so you can fit more indexes and documents in memory, you reduce the latency. To lower the recovery time objective, because when you have shards, you can parallelize the restore and therefore make it faster. Also, if you need to fulfill geolocality requirements, you can, with the Atlas Global Clusters, then that's very useful. I think we had an example this morning that was presented with data in Germany and data in London, for example. Or if you're self-managing your cluster, you can use sharding to tier your data to have a more better balance for performance and cost. So, to summarize, 3 best practices: use batching with insert many, and the unordered API for faster write throughput. Model the meta field and create secondary indexes to match common query patterns, and configure granularity to fit your use case. So, time series also has some new queries and analytics capabilities. Those are the window functions that allow you to run analytics over a flexible window of time, and also the temporal expressions that allow you to work with dates easier. So you can do differences between dates, additions, and you can also subtract or truncate part of a date. The main benefit is you can do that within MongoDB without having to move the data, let's say, to your application layer and then bring it back. So you can uncover insights and patterns in place without using a specialized analytics solution, for example. Here are some examples of window functions. In the SQL world, I believe these are called SQL analytical functions, and the windows are in function of the rows. The nice thing is in MongoDB, it can be in function of the time. So you can do a 15-minute moving average window function, for example. And besides the simple use case functions of running some moving average, we also implemented more advanced ones, such as derivatives, integral, or exponential moving average. This is an example of a window function calculating the total sales by state for cumulatively for different years. Temporal expressions, we have basically 3. The add, that increments or decrements a date by a specified amount of time units, 5 days, for example. Date diff, that finds the date-time difference between 2 date objects, and that truncates part of a date. So, for example, if you have the year, month, day, hour, minutes, seconds, and so on, you can truncate that just up to the day. And that can be useful if you want to plot histograms or do binning of data to calculate, for example, the sales in windows of 5 minutes, for example. This other example combines a window function and a temporal expression or operator with the date trunk. And what I'm doing here is I have about 500,000 invoices, and I'm using this to calculate the total sum of the amounts of the invoices per year using date trunk to group them per year, and then I sort them in decreasing order. So you see how easy it is to calculate something like this with time series. Densification, again, this is in 5.1, it's new. And time series data has gaps in it usually. And for the analytics to work, those gaps need to be filled in. So now we have a new aggregation that allows you to fill in those gaps either by carrying the last value forward or by filling the gaps with constant values like zero filling. And in this example, it's densifying the timestamp field to get 5-minute granularity for series defined by meta location and model. This was already announced on stage, so it's the data archival. It's automated for time series collections now, so if you use to Atlas, it will work exactly as you expect. You set the online archiving, you set how much time you want this to archive, let's say 7 days. So after 7 days, it will archive the date that is older, and it does that in a fail-safe manner, and also deletes the data once the archival is completed. That data goes to an cloud object storage, which makes it very cost efficient. All this removes the overhead from your developers, and you can still query the data using the federated query capabilities we have in MongoDB. So why would you choose time series collections over regular collections? Well, for time series data, of course, but what we saw in the challenges, MongoDB solves all of these challenges with the capabilities I just showed you. Besides that, you can have a reduction in index sizes, a reduction in I/O for read operations, a reduction in the overall storage size, and you get efficient ingesting, querying, and expiring time series data. The performance is comparable to native time series databases. So you don't really need a native time series database to do time series. You can do that with a time series collection in MongoDB. And it's faster than if you model time series by yourself using a regular collection. And many of our customers have already been using regular collections for time series in the past. So this is great if you're already using time series as well. And why MongoDB for time series? Well, you can leverage the MongoDB application data platform. So besides doing all of the things I talked about, like window functions and online archiving, you can also visualize the data using MongoDB charts. You can also take advantage of Data Lake, for example. All of this in a secure multi-cloud environment. So all 3 cloud providers, more than 80 regions. So when we talk about MongoDB for time series, the MongoDB, you can have flexible schemas. So you can use rich data models. You can change your models faster. You can also include objects or arrays if you wish. Platform integrations, I already talked about online archive, charts, all the things you get aside from time series itself. The scale, so you can scale either vertically or horizontally with MongoDB, and now the sharding is available as well for time series. Data lifecycle management, so we handle everything from ingestion to archival of the data, going through visualization, and you get that out of the box with MongoDB Atlas. And data coupling. So even though you've archived your data, you can still perform analytics of your historical data alongside your real-time data with the federated queries. And your data is sitting next to all your other data in MongoDB. So you have your time series collections, your regular collections, and you can blend those as well. Without going outside, you can do that in place. So go try it and see for yourself. It's very easy to get started, and thank you for your time.
Thank you very much, Danilo.
Are we early?
We are earlier. We're certainly earlier than you were expecting to be. So I think we've got a good, we've got 5 minutes, a solid 5 minutes of questions here, and I am slightly unprepared. Please excuse me. So we have had some good questions come in and swap cards. So I will start with what I suspect is an easy one. Does it work with PyMongo?
Yes, it does. So I don't remember the exact version. I think it was 3.12, but it is supported, and you should have a look at the documentation for PyMongo.
Great. I suspect people have been working with MongoDB for a while. There's some people maybe sort of asking themselves this question. Is time series implemented using the bucket pattern? Yeah,
that's a good question. So behind the scenes, the optimizations I was talking about is an automatic generation of the bucket pattern, so behind the scenes. So it is, but you should not implement the bucket pattern on top of time series collections, because that would be going at odds with the actual time series collection.
It's like Russian dolls, putting buckets within buckets.
Yeah.
Can we easily migrate a normal collection to a time series collection?
Yes, you can. And something to keep in mind is you might want to make sure that when you do that, that it's ordered. So because we are storing it with the primary index on the time, so you would want that to be as ordered as possible, because that increases the query performance later on.
Good to know. Can you delete the data if it's on an online archive?
Good question. So I've had that question before, funny enough, while I was outside in the booths. So right now, you cannot, but we are working on it, okay? So right now, you can only delete all of the archive.
I think it's been great to see the progress coming with 5.1, and it's just very exciting kind of rounding out the feature set with time series collections. That's just awesome. There's a question here which I don't entirely understand, so make of it what you will. Can your timestamp key be within an array of objects?
It has to be of date type, so I would say no, it has to be a date. And that's because we use it for the primary index, we use it for the optimized storage, so it has to be of date type. It cannot be any other data type.
Okay. And finally, we have a question which I accidentally skipped towards the top. So, new time series features look great, but MongoDB's millisecond precision can be limiting. Are there any plans to increase the precision without having to resort to other data types and missing out on the new features?
Millisecond precision. I wonder where that's coming from, because we do support decimal 128, which is extremely precise and used for the financial sector and engineering calculations. So not sure I understand the question, but yeah.
Okay. Well, I guess the questions are going to stay up, so there's always a chance to come back to that later. Maybe Chris, who asked the question, can expand on it.
Sounds good.
Well, thank you very much. As you know, I'm really excited about the time series stuff, and I learned lots of stuff in this talk. That was, if we could have fit this into the 3 minutes we had in the keynote, it would have been incredible. Thank you very much for coming, everybody. If we could have another round of applause for Danilo, that would be.
Thank you.